welcome to our 7th learning workshop over chemical thermodynamics for Chemistry 1412. So we're just going to jump right into this question. So sodium reacts violently with water according to the following equation. The resulting solution has a higher temperature than the water prior to the addition of sodium. What are the signs of delta G, delta H for this reaction? So as you mentioned, delta G has a relationship to the energy or the flow of energy in a reaction, but specifically it gives free energy, or the reason why it's called free energy is it refers to the energy available to do work, the energy available to do work in the chemical substances. So the change in free energy is the change in available energy to do work. So if the change, so what delta G helps us determine is if this reaction is spontaneous or non-spontaneous. Because of the law of conservation of energy, you can't just magically create energy out of nothing, right?
Mm-hmm.
Energy has to is neither created nor destroyed. It is simply changed. It changes forms. So,
and to add
case,
to
yeah,
Professor to Professor DePaz, what kind of a parameter is delta G? I mean, so now we understand that it has to do with free energy and the ability to do work. But what kind of a parameter is it?
Parameter? I would assume that.
Go ahead.
Oh, sorry. I would assume that it will give the direction, so to speak, of where the free energy will go to within the system.
Yes, you're correct, but maybe my question wasn't accurate enough. But basically, we like you to understand that it is a thermodynamic function. So you know, we knew from the past that enthalpy was a thermodynamic function, and you know, I assume you've become somewhat familiar with the entropy function, which is a thermodynamic function. So delta G is a thermodynamic function, and it's associated, like like Professor DePaul said, it's associated with free energy. Why do we use it? Why do we need it? Because really, without this complete expression that describes this particular thermodynamic parameter, delta G, we cannot predict spontaneity. I mean, when you have phase changes, we can just use entropy, but phase changes are just, they're just a part of a process. But as far as chemical reactions go, we need this particular thermodynamic function that's all encompassing of the entropy, which is obviously temperature dependent, and the enthalpy.
Now, one thing to kind of simplify this concept of delta G, you can actually kind of think of it as a certain energy accounting, if you will. Even when you have a certain the reactants have a certain bank account, okay, and that bank account is how much energy they have that they can spend, so to speak. That's delta G. Now, the change in the change in the free energy, the delta G, the change in it is going to be negative if energy was spent. Now, if energy is spent, that means that the reaction happened on its own. It means you don't have to do anything to force that to happen. Because they have the energy when they spent it. They have the money when they spent it, so to speak. It happens on its own. If delta G is positive, that means that energy was put into the account, so to speak. So in other words, energy was added to the reactants so that the products now have more energy than the reactants did. Well, that doesn't happen on its own because the energy can't be created or destroyed. So energy can be spent in the process, but if you're going to add energy to it, The only way you can add energy is by putting it in from an outside source, which means the reaction doesn't happen on its own. It either has
Mm,
enough energy to react on its own, in which case the delta G would be zero, or I mean the delta G would be negative
Okay.
because it's going to spend a little of its own energy that it already has, or delta G is positive, which means it doesn't have enough energy on its own, so it has to get that energy from somewhere else. Therefore,
I
it's
see.
non-spontaneous. Can't happen on its own.
Okay,
Does
I
that make
see.
sense?
Yeah,
So we can.
yeah.
Oh,
Oh,
sorry.
okay, go ahead. Yes, yes, go ahead.
Sorry. So, so when we are able to assume the signs for delta G naught, we can assume whether or not the reaction is spontaneous or non-spontaneous. Yes.
Yeah, exactly. So in this case, from the description, is this reaction spontaneous? Does it happen on its own? Or do you need to add energy to make it happen?
It sounds like it's going to be non-spontaneous because of the negative delta G naught. Sorry, like it.
How do you know it's, well,
Well,
first of all, how do you know it's negative delta G? I think you have your reasoning backwards. You don't
yes,
Oh,
determine you don't determine spontaneity because of delta G. You determine
yes,
delta G because of the spontaneity of the reaction.
correct.
So
oh,
in this case, is this, I mean, if you put sodium in water, will it react?
yes.
Well, then it's
It will.
spontaneous.
Oh, spontaneously.
If you put a piece of gold in water, will it react?
Oh no, it'll be
No. So
non-spontaneous.
that's not a spontaneous reaction. So the fact that this reaction happens and the fact that it happens, like it says, violently, means that
Hmm.
this is a spontaneous reaction. This definitely happens
Okay, I see.
without any help from the outside. You don't have to
Mhm.
run an electrical current through this to make this happen. This is something that'll happen on its own.
Okay. I have to clarify one thing.
Sure.
When I was thinking about the spontaneity I was thinking about its length of the overall reaction, like if it's super lasting, so to speak. So
Oh, that
instead.
actually has nothing to do with spontaneity.
Hmm?
When you're talking about how fast the reaction goes, that has nothing to do with spontaneity. A reaction
Oof.
can
Yes,
be spontaneous and it can be extremely
very
slow.
slow. Yes,
And a reaction
so
can be spontaneous and can be instantaneous. It can happen right away.
yes. In fact, and I'm going to give you an example of a really, really, really slow spontaneous reaction, and it's the conversion of graphite to diamond. So obviously, graphite is a very cheap material, and diamond is very expensive. But in our lifetimes, we're not gonna see it happen. But it still occurs. It's just on a much smaller.
Well, in the case of diamond, diamond is less stable than graphite. So diamond on its own will convert to graphite, but it happens very, very slowly, which is why, I mean, under ambient conditions, under standard temperature and pressure, diamond, which is, obviously the beautiful gemstones, whatever is going to convert into, dirty graphite like coal. So, but fortunately for us, when you buy a diamond, that process takes a very, very long time. So chances are you're not going to see any imperfections in the diamond over your lifetime.
Ah,
Yes.
okay. I see. I see.
So,
Which
so
actually
a
brings.
reaction can be spun, and we'll do the calculations in the next problem. But uh,
Mhm.
whether or not it's spontaneous or not tells you nothing about the rate, nothing whatsoever.
Okay, I see. And again, I apologize for being so underprepared.
Oh no, no, you're totally fine. I mean,
It's
that's
okay.
what this is for, to to help explain the concepts and make them more understandable. So If you come in with a certain amount of knowledge, it's great. If you don't, that's okay too.
And so again, I want to emphasize what Professor DePaul says, because it's a very important concept in chemistry. And last time we talked, and you're going to pursue chemistry, as your field. We have to separate kinetics from thermodynamics. These are two totally different concepts.
Yes. And I apologize for getting that like mixed up earlier.
No, but the fact that you're clairvoyant about it now is good. Okay, so yeah, I think we hammered this question number 1 to death. Just one little thing left over is what can you tell us about the T delta S term?
The T delta S, if you don't mind me breaking it down, T. I need to refer back to the book just to be sure that I'm clear on this. Delta S. Where a T delta S, specifically, the term itself stands for standard entropy change for a reaction, which is a change. I'm quoting it from the book, so if I sound too scholarly, that's why. The change in entropy for a process in which all reactants and products are in their standard states. Since we're like multiplying it with the respective temperature, I would assume that we're going to find the amount, the amount of energy that's either like being like added or.
Well, I think you're taking it too far. So basically, we just want to know what is the sign of T delta S.
Oh, I'm so sorry. Sign.
No, not at all.
For question 1.
Yes, what is the sign? Because you actually appropriately determined the sign of the other two, but you normally when we do such problems, we determine the sign of the first term, and then we determine the sign of the second term, and then we do the addition or subtraction, and then determine the sign of the Gibbs free energy thermodynamic parameter. But so what is the sign of T delta S?
Okay, sorry about that little mistake there.
No problem.
We did specify that it would be. We did specify that the Gibbs free energy is negative, correct? I hope I didn't.
Yeah, but suppose we don't know that. I mean, yes, I mean you were able to figure it out, but suppose we don't know the sign of delta G. What we normally do is we determine the sign of the first term, and then we determine the sign of the second term, and then we do the math, the qualitative math, subtraction or addition, and then we determine the sign of the Gibbs free energy change.
Oh, okay. I have to apologize for that.
And just as one more clarification, because Victoria, you mentioned something that I just wanted to just you mentioned negative delta G. You thought that was non-spontaneous, but negative delta G is actually spontaneous.
Right.
Negative delta G is spontaneous. A positive delta G would be non-spontaneous.
Right.
Okay,
And the reason is because a positive delta G means that you're adding energy to the system. To add energy to the system, that means you have to you have to do work on the system. In other words, you have to add energy from the outside. Okay? So it's not something that can happen on its own. If it's a negative delta G, that means that the process will use it will cause the reactants to lose energy, and it can lose energy on its own. Uh, they can lose energy on their own, and they can react to do that, but they can't gain energy on their own without getting help from outside. Does that make sense?
Yes.
Yes.
Okay, so now you already determined the sign of the first term. Now, please determine the sign of the second term.
I would assume it to be a positive, so to speak.
Why do you say that?
Oh, I must apologize if I'm really messing up today.
No. Actually, you may be correct.
Oh, thank goodness. Whew, I thought I was off again.
No. But I'd like to understand why you chose that sign.
Well, because since the reaction is exothermic, I'm going to assume that we have a larger sorry, we have a larger amount of movement, and so to speak, and so therefore interaction with within the
Well,
given.
can I stop you here? But you already iterated on the first term, so we don't need to reiterate the.
Oh, sorry.
Not a problem, not a problem. But otherwise, you're on the right track, because if we look at the phases on the left-hand side, they're solid and liquid.
Mm-hmm.
And then the phases on the right-hand side are aqueous and gaseous.
Mm-hmm.
So, is there more disorder on the reactant side or the product side?
Product side.
Okay, very good. So then, based on this assessment, is delta S positive or negative?
It shall be positive because it
Perfect,
is increasing. Mhm. Yeah,
perfect. So
that's what I tried to like specify, but then I realized like I was being really wordy.
no, it's good. So if delta S is positive, um, what can you tell me about, let me get a red pen here. What can you tell me about this term here?
About temperature.
Yes,
Oh,
yes. So I'd like to note the sign of
oh,
T,
this, oh, sorry.
yeah, T delta S, yeah.
I would assume that it would be a positive then.
And then what is positive times negative?
Oh, a negative.
All right, so I'm going to put a negative, and then I forget, what did you determine was the sign of the first term?
The enthalpy term is what you're saying?
Yes,
Yeah,
yes.
the delta H.
It would be a negative.
Okay.
Yep.
So a negative, let's see, how do we do this? A negative, we already accounted for that negative. A negative plus a negative is equal to a negative. So we
Yes.
did it.
Oh, I got a couple. Oh, I see. I'm so obvious.
um, no, it's actually a fun problem, but thanks for figuring it out.
Yeah, basically, you're looking for, when you're trying to determine delta S, to determine if the things are more disordered, you're looking for phases of matter. that would be there would be more dispersal. So like aqueous NaOH, well, that's going to be a lot more dispersed. It's going to be a lot more spread out. There's different ions and particles that are all over the place and moving more freely than sodium metal. Likewise, you have a gas formed, and gases are always hugely more disordered than any sort of liquid or solid because gas particles
Yes.
move so very fast. And because they move very fast and they're all spread apart, um, they can have many more, shall we say, microstates, because that's ultimately what delta S is all about. S
Mm.
itself, the value of entropy, is a measure of, in a certain sense, it's a measure of disorder that's based on the number of microstates. So, if you think about a microstate as being one possible set of positions and energies of all particles within the system. Okay, so one possible set of positions and energies of all the particles in a system. So, so there's, if you think about all the massive number of particles in a gas and all the positions and energies and such that they could have, um, and the number of microstates is an astronomical number.
Mhm.
It's a quantity that's quite large. But if you think about just generally speaking, and so we kind of think of it in more qualitative rather than quantitative terms. If you think about, like, for example, sodium metal, well, there's only so many positions and energies those sodium metal atoms can have because they're solid. They're kind of locked into place, right?
Mhm.
And they're still vibrating a little bit, and so they have a little bit of motion and such, but they're not. It's not like they can be anywhere that they want to be. Whereas the hydrogen gas, those gaseous molecules, they can be all over the place. You have they're flying around in the air. They're not contained by any specific container unless there is a container there. But even then, they're moving around at such fast speeds that energy can be like I mean the different number of possible energies it can have is just um and position because they're both vibrating and they're stretching and bending, and then they're also moving translationally, in other words, across the room, so to speak. So it's pretty clear that a gas molecule is going to have a lot more possible entropy, a lot more possible disorder than a solid particle, right?
Yes.
So
So
I don't know.
I,
I just wrote what Professor DePaul said. I just wrote it mathematically. So essentially, the entropy of the solid is less than the entropy of the liquid, which is much less than the entropy of a gas.
And you could
wow.
include aqueous there as well, which would be greater than the entropy of a liquid, but less than the
Uh-huh.
entropy of a gas.
Yes, you're right. You're right. We should include it. I'm going to include it right here. Insert it right here, like that.
Very good.
Uh,
Thank you.
Thank you guys very much for like taking it step by step to explain.
And because we are talking about this, Professor DePaul, can you take us to the last problem? The last problem, I believe, is problem number 9.
Here we go.
Let's see, 8. Let's see. Okay. So, Ms. Chavez, we'd like you to tell us which statement is true and which statement is false. A, the reverse of a spontaneous reaction is always non-spontaneous. True or false?
Let's see. The reverse of a spontaneous reaction is always non-spontaneous. I would reverse.
I know what you're thinking. Whenever you see the word always, it makes you kind of a little bit concerned to
Yeah,
say.
yeah. I'm like always. Hmm.
But if you think about it this way, whenever you have a delta G of a reaction, if you flip the reaction, it flips the sign of delta G. So,
It would be a true then.
Yes.
yep,
Ooh,
Okay, so moving forward, a
sorry.
spot.
There was like a big pause there.
Yeah,
I thought my audio didn't come in.
yeah, yeah. Yeah, we have to deal with technology.
No, no, you're fine. You're fine. I was like wondering if there was no like like uh, if there was no slow delivery of my message.
Okay, got it. So the next one, a spontaneous process always move towards minimum energy.
Let's see. As into like release said energy from the system. I would assume since this releases so much energy, and just to have the reactants be in a more stable chemical form, I would assume that B is true as well.
Yes, but you do not have to assume because it is a statement of a fact. So so you can say, indeed, statement B is correct. Just like if you have a ball on top of a hill, it'll roll down to the ground. So we
Yes.
don't have to assume that it does. It just does it because it's trying to seek its minimum energy. And why does it do that? Why does a ball on top of a hill roll down to the ground? Why does it do that?
Let's see. Oof. That would be because in its placement within the system,
Gravity,
gravity.
right,
algorithm
right.
should have
Gravity
developed
like
it at
makes
the
it
time.
much more unstable, so to speak, with its
Um,
potential energy. Oh,
okay,
sorry.
I'm sorry, I didn't hear you, Professor DePaul.
Oh, I just said, I was just going to say because it felt like it at the time.
Too funny. Too funny.
It felt like it. My goodness.
Oh gosh, that is too funny.
Yeah, no, yeah, you're right. It absolutely gravity just brought it down. It was attracted to the center of the Earth and that kind of pulled it into its lowest position. Yeah.
Yes.
But what about, so let's look at number C, or number C, letter C. A non-spontaneous process cannot be caused to occur. Is that
Oh,
true?
now that's a good one. Let's think about that. It's kind of tricky.
A non-spontaneous process cannot be caused to occur. Um, uh, uh, by cause, this means like there was like additional like input or no like
Yeah.
additional assistance to cause a reaction.
Yes,
Okay.
it's not saying a non-spontaneous process. It's not saying it cannot occur by itself. It's saying a non-spontaneous process cannot be caused to occur. In other words, even with the input of outside influence, outside energy, a non-spontaneous process cannot be caused to occur. Is that true or
Uh,
false?
okay. I would assume that this is a true, a true, so to speak.
Actually, it's false.
Oh no, I got it.
Non-spontaneous,
I agree. I agree with
non-spontaneous
Professor DePaul.
processes, they can't occur by themselves. A non-spontaneous process can never occur by itself. However, if you if you pair if you pay the energy cost, so to speak, if you pair a non-spontaneous process with a spontaneous process, then you can cause it to occur. Think of it like this. Um, your room getting clean is a non-spontaneous process. It's not something that happens on its own. Right? You have to actively work to make it happen. But if you pair that with a spontaneous process, such as um, when you when you intake food, when you eat, the processes that in your body carries out, which transform that food into energy, are spontaneous. So that spontaneous process of giving you energy allows you to do the non-spontaneous work of cleaning your room. Does that
Oh,
make sense?
yes. Can you repeat your statement again?
Um, yeah. So if when you take in food, the spontaneous processes in your body which convert that food into energy, you can use that energy then to do the non-spontaneous process of cleaning your room.
Okay, I see. I see.
And likewise, there are a lot of cases in which, if a reaction will not happen on its own, what a lot of times will happen is industrial chemists will pair a non-spontaneous reaction with a spontaneous reaction. The spontaneous reaction provides the extra energy, and then the non-spontaneous reaction is pushed along
Oh,
using
I
that
see.
energy.
So it's kind of like the domino effect, so to speak.
Exactly. It's not going to fall on its own, but if you add a little energy to something else, then that energy can be used to cause something else to happen. Yeah, in a certain sense, yes.
Oh, okay. I
And
was
I have an
imagining.
ex
Oh,
Go ahead.
yes.
yeah. I have another example, but mine is very simple, so you promise not to laugh at me. So,
Oh, I'm
I make no
um,
fine.
promises.
so remember that ball that rolled down to from the hill to the ground because of gravity?
Mhm.
I can roll it, I can use my hand and my muscle power and push it back up the hill if it's a small hill, obviously. So, in a sense, I'm forcing that ball to, I'm putting work to, to do work against gravity. So that's my dumb little example.
No, that's
Oh, no.
not dumb at all. But of course, that energy has to come from somewhere, and that energy, of course, comes from the food that you eat. And the energy from the food that you
Yes,
eat has to come from somewhere as well. So that comes from
yes,
the uh, the plants, and the plants have to get their energy from somewhere, and that comes from the sun. So there's this
yes,
cycle of energy um, that goes through, and eventually the buck has to stop somewhere. But but
yes,
basically, yeah, there's this cycle of energy that we're all that to make a non-spontaneous process happen, you have to get help from a spontaneous process. Because ultimately,
yes,
keeping your body ordered, keeping your body in good health, is actually a non-spontaneous process. It's not something that happens on its own. That's why we constantly need to eat. We constantly need energy. We constantly need, nutrition, vitamins, and nutrients, and things like that in order
yes.
to keep our body healthy.
Now, if this is a concept we could convey to the students that if they ate a healthy plant-based food, they could do better on tests, you know, then, then we would really be conquering the world.
We would
But
be.
So there we go. So C is indeed false. And we make non-spontaneous processes happen all the time, but they require outside energy. They can be caused, but they require outside energy. And sometimes it's due to just an infusion of electrical energy.
Uh-huh.
Sometimes you can, when that's called electrolysis.
Right.
But yeah,
And that'll be fun when we get in the next few weeks, when we get into electrolysis, we're going to come and pivot back on this concept of non-spontaneity and forcing it to occur.
Okay.
what about our last statement here? A highly spontaneous process does not have to occur rapidly. True or false?
Okay, so this one, I remembered from what for what Dr. Asgharian specified earlier. This statement is referring to the rates of the said reaction, which is in kinetics, and so. However, though, spontaneous, as she has specified, spontaneous processes can occur at very slow rates. So for D, this will be true, so to speak.
Excellent. Good job. Thank you for reiterating our statement and concept on this. You're a very good student.
For bonus
I'm
points,
best.
for bonus points, what is it that causes the reaction rate to be fast or slow?
Good question.
If
Oh,
it's
okay.
not
Well,
delta G, what is it?
if it's not delta G, I'm thinking more like of the factors that would affect like reaction rates, so to speak. So for me, I'm thinking of like changes in temperature, concentration, so to speak. Uh,
Yes.
uh,
Yes.
oh,
And
catalysts as well, which
yes.
will lower the activation energy, and also for like a
Oh, you
gaseous.
hit the big one right there.
Oh,
Activation energy. Activation
Yes.
activation.
energy is the single biggest factor
Yes.
determining the rate of a reaction. And then, of course, yes, at higher temperatures, the substances will be more easily able to overcome the activation energy. But
Yes.
that's the biggest factor that determines whether or not a spontaneous process will be very slow or very fast.
Okay.
Exactly. Great job. So,
Okay,
I,
so do we want to? What do we want to do for? Do we want to actually just shoot up to number 8 and kind of hit that on our way back?
I like that.
Okay,
Sure.
so
So,
ice melts. So let's think about this. What is the sign of delta H? Is it absorbing energy, or is it absorbing heat, or is it releasing heat when ice melts?
It'll be absorbing heat. So I would assume that delta H will be positive.
That is correct.
Or assume. Sorry. I would say with confidence.
yes.
Delta H.
Excellent.
There
Excellent.
you go. Now, what about delta S? So, and when ice melts, so when ice melts, what is the sign of delta S? The level of disorder, the entropy.
Uh, since the molecules are dispersing over a larger volume, I will assume I will say that delta S is positive. Since it
Yes,
is
because it goes from a solid to a liquid, which is a more disordered state. So it is more disorder, has more microstates, and therefore a higher delta S. So positive change in delta S. Very good.
Well
And
said.
then what about the overall, which is the delta G, for the melting of ice at 5 degrees Celsius?
even though we are subtracting it, given that both values are positive, I'm going to say that the Gibbs free energy is actually, oof, sorry,
Well, I'll tell you
But,
this. Let me see if this can help you out. When you're
mhm,
analyzing this, you have to go beyond the mathematics. You have to think about this. Because in truth, we don't know precisely how big the delta H value is, and we don't know how precisely big the delta S value is.
yes.
There's not enough information for that. All we know is that it's absorbing energy and it's becoming more disordered. A positive delta H value would lead towards non-spontaneity, but a positive delta S value would support uh, a spontaneous process, or it would contribute towards spontaneity. So the overall negative T delta S is negative because T has to be positive and delta S is positive. So minus T delta S is going to be make the whole thing negative. So you have a
Oh,
positive delta H and a negative delta S value. Those two are opposites. They're fighting each other. The delta H wants it
Yes.
to be non-spontaneous, but the T delta negative T delta S is pushing towards it being spontaneous. So you can't tell mathematically which one it's going to be. You have to rely upon your reason. And that is, well, you know that a negative delta G corresponds to something being what? Spontaneous or non-spontaneous?
let's see if my memory's right. I would assume spontaneous,
Yeah, negative delta G is spontaneous, and a positive delta G is?
non-spontaneous.
Exactly. So you can actually determine whether or not delta G is positive or negative just by merit of the fact that it is either a spontaneous or non-spontaneous process. So if it's 5 degrees Celsius, is is it if it's 5 degrees Celsius, is delta G spontaneous?
Oh, that's right. Because you're dealing with standard enthalpy, or sorry, no, standard conditions.
Uh, yes. Well, and just think about this. Will ice melt at 5 degrees Celsius?
Oh no, of course. Is
No.
oh wait, oh
What's the
sorry.
melting temperature of
Like
ice?
negative 5 degrees Celsius. Yes, it will melt.
Yes. At 5 degrees Celsius, it will melt. Now, if it was negative 5 degrees Celsius, then no, it wouldn't melt, would it?
Yes.
That would be a non-spontaneous process. But if it's 5 degrees Celsius, then it is going to melt. It will be spontaneous, and therefore delta G will be
Uh, uh, um, delta G will be a negative.
negative. There you go.
Yeah, Professor DePaul, I like how you analyze this because this is actually, I mean, this is actually a case where you cannot just use the signs of the first term and the second term of the equation to determine the sign of delta G just because they're opposing each other. So yes, I was thinking, what do you do? What do you do? Here, enthalpy is positive and T delta S is negative. So what do you do? What do you do? What do you do? And then, yes, Professor Tabas said, well, you just have to kind of put your brain cells in work. You just can't rely on the mathematics here. And you know that ice melts above 0 degrees. So if it's this is 5 degrees. So it happens spontaneously, therefore delta G must be negative. Yeah. Okay, good.
Yeah, it's one of those key things that I think sometimes that, especially in the realm of physics, and especially at the higher levels with the PhDs and such, there's a little bit of a danger. Um,
Yes.
Mathematics is an extremely useful tool for
Yes.
processing reality, for processing relationships, but
Yes.
mathematics is not in and of itself reality. It is simply a
It's a,
symbolic representation of
it's a
reality
la-
that,
I agree. I agree. It's a language. It's a language that chemists and physicists love to use to make their life simpler, but it's a tool. It cannot replace describing nature. Yes.
exactly.
Oh, good. We are good. Let's go now to number 7. Let's see, number 7.
All right, so let's go ahead and take a look at the next one. I'd like to go back to the screen, to problem 2 or 3.
Okay, so let's go back to problem 2 is good. Yeah.
Okay, sounds good. And I'll let you lead off on this one.
Okay, let's see. Okay, so yeah, I think we briefly talked about this as well. We have a process of it's a phase, it's a solid phase transition to another solid phase transition. It at graphite to diamond, and we are given the standard thermodynamic parameters of enthalpy and entropy. And so what can we say about the conversion of graphite to diamond at STP? So basically, what we're looking for is, does this process occur spontaneously or not?
Um, I would say that this reaction occurs non-spontaneously.
Let's see. See, I can't do it as fast as you, so I'm going to go ahead and
I have to apologize if I'm working a little bit too fast today.
that's what we want. Okay, so what is the sign of the first term?
Enthalpy, it'll be positive.
Okay, and what is the sign of the second term?
It'll be negative. However, though, oh, sorry. There's also another detail that we'll have to consider. I call me silly. I just now notice it. Um, uh, it is the units of energy for enthalpy and for the standard entropy, so to speak. Enthalpy is kilojoules, while the standard entropy is joules per Kelvin.
Okay, yeah, that's okay. We are not worried about the units now because right now we are not doing calculations. So we
Oh,
just want to, figure out whether this process occurs at STP or not. So you gave me the correct sign for the first term. What can you tell me about the sign on the second term?
the second term, it would be negative.
Okay, so what is negative times negative?
Oh, positive. That's right. Let me bring this little. Let me bring my little pencil here. I was thinking of this specifically. I forgot to consider this.
Yes, that's good. That's good. And so then a positive, um, a positive and a positive is positive. And so let's see, what was your response? You said you already gave me the response before I had to evaluate it. You said based on this data, graphite cannot be converted to diamond. Is that what you said?
Cannot be converted to diamond. Oh no, it appears I have something mixed up.
So let's see. Okay, so we evaluated the thermodynamic parameters. Now, based on this data, what can be said about the conversion of graphite to diamond at STP? So if you can tell me, does it occur spontaneously or not?
It would be non-spontaneous.
Oh, good job. Is that what you said before I started out the problem?
Yeah, I did the calculations earlier. I was worried about my like units though, but then I realized, like kilojoules to joules, it's going to be a larger amount of joules, so it was still positive
Oh,
towards the end.
ex excellent. You you beat me to this. Excellent.
Oh, I'm surprised.
So yeah, I mean, it's like Professor DePauw explained an hour ago. Yeah, graphite does not convert to diamond. But lucky for us, diamond, the reverse of the process obviously is spontaneous, but lucky for us, it occurs in such a slow time scale that we don't need to worry about it. I don't have any diamonds, but for those that do. Okay. Okay, good job. Now let's go to number 3. Let's see. Okay, now we have a quantitative problem. Calculate the standard entropy of formation for 1 molar of solid sodium bromide from the elements at 25 C. So the first thing we need to do is to write a balanced chemical reaction because we're going to use the number of moles to find the delta S. So could you, Ms. Chavez, could you please write the chemical reaction for this problem?
Yes,
Thank you.
I shall type it out if you don't mind me.
Perfect. Perfect.
I would assume that we'll have to. Oh, my throat. Sorry.
Are you thinking the entropy of the products minus that of the reactants?
Yes.
Okay. So would you like to write it out?
Yes. I shall type
And
it out.
and if you prefer to type, I mean, I see it. I see it pretty well with typing.
Oh, okay. Thank you. It's just that it's just that from my side, the font looks really small.
Yeah, but I have increased it so I can see it. I have increased the size so I can see it.
Okay. There's also another formula that expands more on this.
Uh-huh.
It says like a delta S naught reaction equals sigma, which is like base sigma or the sum of the stoichiometric coefficients times by the standard entropies of the products minus the sum of the stoichiometric coefficients times the standard entropies of the reactants. Do you want me to
Exactly.
as well?
Exactly. And
Sorry?
actually, really, it's the same thing. It's just that you have to keep that's why we wrote the chemical reaction. We need to keep in mind the number of moles. So I mean, what you have written should work, but just don't forget to account for the number of moles.
Yes. Oh, do you want me to write down my steps?
Actually, give me the answer. I want to see if it matches mine.
Sure. I got negative 81.2 sorry, joules per Kelvin.
Okay, so I got minus 40.6. So let's see which one of us is correct.
It might be a mistake from my
40.6, right?
calculator.
So can you just read me your equation, like when you plugged in your numbers? Can you please read me what you got?
Oh, okay. So for delta S naught for the reaction,
Uh-huh.
I got for the products
Uh-huh.
2 times 86.8,
Yes.
and minus,
Yes.
and then this is in parentheses, within parentheses,
Uh-huh.
2 times 51.3 joules
Yes.
per Kelvin, plus
Yes.
um, um, plus 152.2.
Aha. That's. Oh, the plus is in parentheses, right? Because
Yes.
okay. So because so I have it like this: 2 times 86.8 minus 2 times 51.3 minus 152.2. And so you have the same equation. So why do we end up with different numbers? Let me do it again.
Uh, um, uh, uh, um, uh, the formula specified that it was the summation of the enthalpies or enthalpies. Oh, sorry, of the entropies for the reactants.
Yes, but it's a plus sign, but it's a minus because it's being subtracted. You see what I'm saying? So, for example, let me see. Let me write it. Let me see if it matches yours. Give me 1 second here. Okay, so basically 2. Is this how yours is set up?
Let me see. Oh, I'm using my if you don't mind me bringing out my little pencil here. Um,
Yes.
for me, I almost did
Uh-huh.
the thing. However, though, I put these uh, the values here within the respective parentheses. This is for the del. This
Oh,
is for the.
well, okay. If so, so so let's see.
By the way, I just dropped the file for this set of problems in the chat. You can click on that and
Oh,
download it.
oh yeah, yeah. Thank you, thank you.
Thank you.
Let's see. Ah,
Oh, if you don't mind me, I could type out how I put in the numbers.
see,
There you go.
that should be a, yeah,
So it should come out with a negative. Yep, it
yeah.
should come out with a negative.
Because right, it should come out with a negative, and so Ms. Chavez got a negative 81.2. I got a minus 40.6, and I think it's because Ms. Chavez,
Mhm.
this you made a little mistake here. I think so.
Oh,
Instead of a
mhm.
plus, you had a minus, which would account for.
Oh, you think that I subtracted the 152.2 is what you're saying?
I mean, your bracket. Okay, so basically, it, you know,
I can
let's see.
type down exactly what I put in.
I got negative
Uh-huh.
81.2.
Oh, you got. Oh, I'm sorry. So you got minus 81.2. Okay. Let's see. Well, then two wins over one. I'm sorry, you have been correct.
No, no, you're fine. You're fine.
It's minus 81.2. Thank you guys.
You're welcome.
Okay. So very good. Now we can go to the next one. So we need to find the standard free energy for this reaction, and the free energy formations are given for the products as well as the reactants. So let's go and plug and chug and see what we get.
Like, ooh. Again, I apologize for my nasty handwriting.
No, yeah, only Professor DePauw knows how to write so beautifully on these platforms. But I can read yours.
I have to apologize, but I don't know how this like little like blue line got on the sheet, and I
Yeah,
can't read it.
that's one of the beauties of this platform. 8. Okay, I got an answer.
I got the same thing as well.
Oh, excellent. Okay, excellent. Now let's go to.
What about Mr. DePaul?
If both of us agree, then I'm sure he won't complain.
Okay, making sure.
Let's go number. Okay, so at high temperature, boron carbide vaporizes according to this equation. Okay, write the equation that describes the relationship between delta G standard and delta G. Okay, so remember, so basically remember that when we have a system at constant temperature and pressure, spontaneity occurs in the direction that lowers its free energy, which it explains why reactions go until they reach equilibrium. And equilibrium essentially is the lowest G, lowest free energy that's available to a system. And the G of the system, or the free energy of the system, changes as reaction goes. So it means that most reactions occur under non-standard pressures and concentrations, and delta G naught just refers to standard conditions. So the relationship that would accommodate non-standard conditions looks like this. The general way of writing it is going to take the reaction quotient into consideration. It looks like this. Q is the reaction quotient. And so again, it just means that we're working in non-standard conditions, which is really the reality for most situations. And so now that we have to write an equation that describes this. So how about B is the gas? So we know that the solid states don't enter equilibrium. So we really have to only account for the gas phase, the boron in the gas phase. So we can say basically the Q is the natural log of the partial pressure of B. So all of this remains the same. Delta G is equal to delta G naught plus RT natural log of the partial pressure of B. However, there's 4 of them. So with the law of natural logs, the 4 is going to come in the front. This is a 4. 4 natural log of the partial pressure of B. Essentially it's natural log of PB to the 4th, right? Because of the 4 right here.
Mm-hmm.
So we can take the 4 from the exponent and bring it down, like 4 RTLN PP. So this is the answer.
Oh, I see.
So again, the concept here is that we're dealing with non-standard conditions. The Q reaction is the reaction quotient. It's reaction quotient we saw a few weeks ago. Um, it's um, it's different from K because K refers to the equilibrium constant, and Q refers to the concentration or the partial concentration of ions in solution, or else the partial pressure of gases. And we remember that the solid state does not enter equilibrium expressions. So, so that's it. Does it make sense?
Yes.
Okay, perfect.
Oh, I think it's. Oh no. I think it's almost time for the session to end though.
Oh, okay.
I'm sorry.
Okay, yeah, no problem. So there's only two problems left, but I believe, no, like 6 and 7. Hold on. Yeah, I believe that you have all the tools to finish problem 6 and 7. If you have any questions, just email me.
Yes, ma'am.
Okay, well, thank you so much for coming, and um, we look forward to seeing you next week.
Bye, y'all. Stay safe.
Bye. Take care.
Well, bye bye.